Hello, this is Dr. Hisham Said. Welcome to this video where we will learn about shear stresses, what type of shear stresses develop, single shear, double shear, how to calculate them, and I'll see a couple of examples on doing that. So okay, 1 minute, and then here we go. Yes. So shear stress is the stress, it's a force over the area, but it's here a force that's generated by transverse loading. And it's created by transverse loading, and the force, internal force, and the shear stress itself is parallel to the cut surface we're making in this member. So we have here like this scissor action, P and P, and they're trying to shear or cut this member. So we do a slice in between these two members. If we do the cut and analyze the equilibrium, we see the left external force here. And once we do the cut, we reveal the shear force V, which from equilibrium, sum of forces in Y, we'll find it's equal to P, or P prime. P and P prime from external equilibrium are equal. So shear stress is equal to that shear force V over the cross-sectional area. And similar to the normal stress, when we say sigma average, here we calculating an average shear stress. And this is more critical even in the case of shear stress because it's only valid in the case when the area is small. So we'll see in next lessons that it actually matters a lot, the shape and the look of the section, and the shear stress will be different at different spots. It's not one single value for the whole area. So we'll revisit that when we discuss the design of beams and shafts from torsion, so we will see that in the future. But because we're simplifying here shear, just introducing the concept, we will focus on the most famous shear action that we see, which is that one applied on bolts or pins. So we see here in the top, this bolt here is resisting the shear action. We'll see that in details. And these pins here are also kind of resisting shear action. But there are two different types of shear actions. So we'll learn now about single shear and double shear. So single shear, this is a shear action that happens in a member that experiences only one shearing, movement here. So if this spring here, this is kind of a support for a platform. We have here the spring with the piston is applying a force on that bolt. And then as a result, you will find that there is a reaction force here applied from the frame onto the bolt. So kind of there is in the middle here, there is one shearing action happens. This here shows you a representation of the system. Two plates or members are connected by the bolt. They have same force applied, and they are causing that shear on the bolt. If I take out the bolt and make a cut between these two shearing forces, I take with me out here one of the external forces in the bolt, and then I will reveal here the shear force resisting it. So let's see here. This is a video showing here the shearing of a bolt in action. You can see here it started sliding, and then here you go. That's now this bolt here is gone. It did fail under shear. So that was single shear. Now double shear, from its name, now we have that member is experiencing double shearing actions. So there's one force pulling the member, and then there are two forces pulling from the other side. There's two shearing actions between these two forces. So another example here, you see this spring piston is supported by the bolt, which is supported by these two brackets. Kind of a different representation, but similar to it. So we have here these two plates, connecting plates or splicing plates, are transferring that pushing or pulling force F and splitting it between the two splicing plates. Now if we think about it, there is a one shearing action between this force and half of it on this way, on this side, and another shearing action happens on the other side. So now this is why we call this a double shear. So let's see another example of single shear and double shear, which for those of you who bike. So we have the bike here, the pedal, and let's assume there is this loading case where all your weight is going through your one foot and it's applied on one pedal. So we're analyzing here the bolt of the pedal. There's your weight is here, and then the crank is supporting the bolt, so it's resisting it by a counter force here, P. So the idea here is we need to draw a free body diagram of this bolt here, what kind of shear is happening there, and try to calculate the shear force applied there. So let me open this on, alright. So this is kind of trying to zoom in into the bolt, and the idea here is we draw the free body diagram of the bolt. Kind of the dotted lines here are showing the crank arm and the pedal, but I'm more interested into the forces from them on the bolt. So C and C prime are the points where these forces are applied. I'll do a cut in the middle, and you can see here that there's a shear force applied on this cut, and if I do the equilibrium, the shear force will be equal to your weight, or P here, that we have, and it is a single shear. And then tau would equal to the shear force over the cut area, and I just want to emphasize here that this is an average shear stress. Tau average will equal to V divided by VA. So going back here to the slides, now let's see another case where you're actually now standing on the bike, so half of your weight goes on each one of the sides of the pedals, and we're interested into analyzing the crankshaft, this one here. So we're showing only one side of the loading case here. Half of the weight is going here, transmitted through the crank to the crankshaft, and the same case on the other side. All your weight now is supported by the bottom force here from the bike frame on the crankshaft. So kind of this is a simplified version of what I just described, and what we're trying also to do here, similar to the previous example, is to do the free body diagram and analyze the equilibrium here, analyze the shear stress. So this is the free body diagram. I kind of draw here C and C prime. Focus only on the crankshaft and imposing the loads and the reaction. Next would be here to recognize that this is a double shear. You can see here P is split between two sides of that member, so there are two shearing actions happening. If I pick one of these shearing actions and do a cut and draw the free body diagram for it, you'll see here from equilibrium V would equal to P over 2. If I calculate tau average for this shear force, it would be P over 2A. So let's see another example here. So I have here a bigger member carrying 2P and two smaller members connected to it. I'm connecting these two members with each one individually, separately with a nail. So now what type of shear action here? Single or double? If you look at the nail, there is one force flowing here, P, and then 2P here is split between these two nails, so there's another 1P is applied on the other part of the nail here. So force, there's a shearing action in the middle, only one, so this is a single shear. If we revise a little the connection here, and instead of nail we have a bolt connecting all the way through here, if we look at it, the flow of forces, this 2p here is applied kind of in the middle, is a split, and flows through the bolt to the two other blanks here. So if this is 2p, there's a p here, there's a p here, then there are two shearing actions you can visualize between along the length of this bolt. So this is a double shear. So just to conclude here, what's the difference between single and double? It's still both of them are shear. It's just a different way of making that force flow through the connection. So here it's flowing by causing only a single shear. Here it's kind of split between two splicing members that cause the force to be split, and this split means that you have now two double shearing action. Why we do that? Because probably the nail here capacity cannot carry this whole F, the shear capacity of it, so we splice the connection to be able to split the force in over two shearing actions, not one. Also, this connection here is more symmetrical with the double shear than this one. There's some little eccentricity here that might cause problems. So this is more concentric loading than this one. So we covered single shear, double shear. Another type of shear is punching shear. So punching shear here is very common action in shops. So when you want to make a hole in a sheet of metal, you just punch, you have a punching machine. The punching here, the making this hole is just a pure shear action. We want to analyze here how to calculate the shear stress. So we'll go to another kind of little example here. So if I use here, call these dimensions here, the diameter of the hole that I'm making, so punching through the sheet, so punching that circle out of it, and then the thickness of the sheet is T. So the shearing here happens along that surface, that inside circular surface with this depth. So that's my shearing area, and this area is equal to the perimeter multiplied by the thickness. Using the notations I use, so it's pi dt, and now I can see now that my tau is equal to p over pi dt. So punching shear is very common in shops, but also in civil engineering. It's very critical when you have a structure that doesn't have beams connected to columns and then the beams carry the slab. You actually have the slab carried right away on a column. So it's kind of you're holding a piece of paper on a pen, and if you try to push the paper down, then basically the pen will punch through. So this is what happens. Columns punch through the slabs when the slabs are loaded. So we resist that by reinforcement in the slabs and designing to account for that. So this is just another case of punching shear. So the last thing we'll do in this video is kind of trying to meld together, combine the knowledge of normal stress and shear stress in one example, and illustrate that they actually can happen at from the same loading case. So let me pull here the solution for this exercise here. We have a bar that's welded with 60 degrees, and it's being tensioned from both ends by two equal and opposite forces, P. So the idea here is I will analyze either side of either of the two sides of this cut. And so I will decide to analyze the left part, and the weld here is at 60 degrees. Also, what given to me, or I can assume, is the area of that bar, and if the weld here was 60 degrees, so I'll call here this angle theta. So I'm trying to find a relation between the upward angle area A and the weld kind of theta angled area A prime. So from geometry I can say A prime is equal to A divided by sine theta. Now if I analyze the equilibrium internally here, I reveal the normal axial force, N I will call it here, and that will be equal to P from sum of forces in X. Then this is my axial force. Then I will say sigma is equal to P divided by A prime. But that's wrong. If we remember, normal force and normal stresses must be perpendicular to the cut. So what I calculated here is not sigma. Sigma has to be perpendicular to the surface where I'm cutting. So that's not perpendicular. P is not perpendicular here, as I'm showing it. So what happens is I have to analyze here some components of this force. So I calculate the components that is perpendicular. So I have a component that's perpendicular here. It is the true normal force, N, and then there is, if I take out that component N, then I am left out with the parallel component to the surface of cut, which we call the shear force. So now N and V are components of P. So how to calculate these? Again, some geometry here. P, and if you remember from statics, we learn how to calculate component forces, parallelogram method, or using the trigonometry. So please refer to statics to learn how to calculate that. But you see here that N is equal to P sine, the opposite angle here is theta, shear is the cosine component of this. So now I be able to calculate the normal stress, and as a byproduct of this, when I did this breakout of P, I have also a normal shear force that causes shear stress. So now the normal force will cause a normal stress sigma, and now I can say correctly it's equal to the normal force that's perpendicular to the area dividing these two values. So I have here end up with P over A sine square theta. The shear force now, following the true definition of shear stress, is the shear force parallel to the area. I calculate the division of these two values, and I end up with P over A sine theta cosine theta. So be careful of your cut and trying to figure out the stresses at a point. The way you cut at this point makes a big difference, because once you cut and you want to calculate the type of stresses we have, which are normal and shear, you have to follow the definition. Normal, this force should be perpendicular to the cut. Shear is a parallel stress to this cut, and you have to get the components from the internal forces that you can easily calculate. So I recognize that I can easily calculate N is equal to P, but that's not my true N. The N that's perpendicular to the weld needs some geometry calculations here. So with this kind of exercise here, we end up with this lesson. So this lesson here we'll learn about the different type of shears: single shear, double shear, punching shear. We've seen examples of calculating each, and we've seen a conclusion example of kind of trying to relate shear stress and a normal stress in one single case of loading. So that's it. Take care. Thank you for watching.